talk is to draw a connection between these two phenomena. And all of our results are summarized in this diagram on the first slide. And so at this point, it should not make any sense what this diagram is saying, but hopefully by the end, we will at least be able to understand the left half of this diagram. Okay, so most importantly, I want to thank my collaborators. So most of the talk will be focused on this paper with Sento from end of last year. But towards the end, if time permits, I'll also discuss some recent results on using a charge 40 superconductor to do quantum computation with these authors from Harvard. Okay, without further ado, let me begin by discussing the stars of the show. We have superconductivity and the fractional quantum Hall effect. So in textbook, superconductivity is an instability of a Landau Fermi liquid. And crucially, for most circumstances that we care about, the Cooper pairs arise from pairing together time reversal partner electrons on antipodal points of the Fermi surface. And this immediately tells us that any amount of time reversal symmetry breaking should be pair breaking, right? It's bad for the superconductor. And this is the conventional intuition we have. Of course, there are some examples that challenge this intuition, including the discovery of many ferromagnetic superconductors in the early 2000s. But I would say that by and large, right, the normal expectation you have based on textbook knowledge is that superconductivity should abhor time reversal symmetry breaking. On the other hand, fractional quantum Hall effect, one of the most beautiful effects that has been observed in condensed matter physics, crucially relies on time reversal symmetry breaking. In particular, in the old 2D electron gas realization, we need a huge magnetic field to stabilize these quantized fractions of resistance, Hall resistance specifically, as shown in the left plot. So one of the most amazing properties of these fractional quantum Hall states is the emergence of quasi-particle excitations called anyons, which carry both fractional charge and fractional statistics. So naively, based on this textbook expectation, you would think fractional quantum Hall and superconductivity can never appear in proximity to each other, right? The conditions that favor these phases are diametrically opposite to each other. However, we should be surprised, right? It's the whole point of doing experiments is that theorists are always wrong, and experiments will help us disentangle ourselves. And so the major surprise that came out of Mori materials about 3 years ago is the discovery of fractional quantum anomalous Hall effect at zero external magnetic field. So this was first done in the concept in twisted MOTE2 by the Washington group. And later on, Long Juice group from MIT also discovered basically the same set of phenomenon, although the microscopic mechanism is quite different. But they see the similar quantized fractions, and as you can see, the transport phase diagram have remarkable resemblance to each other. So the key point here is that we've removed the external magnetic field. So the system has to spontaneously break time reversal because of interactions. But now, because there's no external magnetic field that's forcing time reversal symmetry breaking on you, you might as well expect that superconductivity and fractional quantum Hall can coexist with each other. So this is just a statement of possibility, right? So what really happens in experiments? So we see in twisted MOTE2 from last year, there's a set of very surprising experiments. Oh, sorry. Actually, this is not twisted. I should first go to rhombohedrographene. So the first set of experiments are from rhombohedrographene. And what was observed is that if you take pentalayer graphene with a little bit of Mori potential, right? The experiments from 2023 already showed this sequence of fractional quantum Hall states. But now if you remove the Mori potential and just look at pentalayer, roughly in the same region in phase diagram, so this is outlined in this red dashed regions that I've included, instead you see a superconductor, and it's a very wide region of chiral superconductivity. So clearly, we don't have access to continuous tuning of Mori potential in the system, but it clearly shows that superconductivity and fractional quantum Hall effect are in close proximity to each other in the same diagram, in the phase diagram of a single material. Moreover, a similar but sort of a similar proximity was also observed in twisted MOTE2 in these ultra-clean samples from Tingxin Li's group from Shanghai. And here we I want you to focus not on, this entire global phase diagram, but let's just think about a fixed line in this phase diagram as zero displacement field. So the displacement field is the y-axis in the phase diagram, and the horizontal x-axis is doping, right? So if you look at the tilted square, right, that is the fractional quantum anomalous Hall effect at Hole doping of, sorry, not at Hole doping, just at Hole filling of 2/3. Okay. So if you deviate from Hole doping of Hole filling of 2/3, you see a wide dome of again chiral superconductivity. And this is also very clear from the transport phase diagram. So you see a quantized 3h over 2e squared Hall resistance and almost zero longitudinal resistance. And then if you dope slightly away towards nu equals 1, you see that both the longitudinal resistance and the Hall resistance will drop to zero, signaling the formation of a superconductor. So again, of course, these two materials are very, very different, but in both cases, we see that fractional quantum Hall and superconductivity exist in close proximity to each other. Finally, experiments are complicated, right? So as a theorist, it would be great if you can find the same phenomenon within a simple toy model that we can study using numerical techniques. And this is indeed achieved in this paper by Mike Zaltau and Taige from last year. And also there are some related works from Liang Fu's group at MIT. And what they observe is you can take the simplest possible model you can imagine for fractional Chern insulators. Basically, you take Landau levels, you take 2/3 filling of the lowest Landau level, and you add a tunable periodic potential such that there is exactly one flux quantum per unit cell in the periodic lattice. So what you can do now is if you set the periodic potential to be zero, you of course recover the standard James state. And now if you increase the periodic potential, and when its bandwidth is much larger than interactions, then you do expect to find a metallic phase. But the real surprise in this numerics is that in between the metallic phase and the fractional Chern insulator, there's an intermediate region, right, intermediate strength of the periodic potential, where you actually see a chiral topological superconductor. And this chiral topological superconductor has this interesting property that if you look at its winding of the pair order parameter around the normal state Fermi surface, you see that this winding has angular momentum 3. So in other words, if you use the intuition from standard BCS theory, you would expect that this winding of 3 implies 3 Majorana edge modes that's living on the boundary of the sample. So in other words, the chiral central charge is odd, and it's a strong topological superconductor, which was, of course, very important for possible realization of Majorana zero modes and topological quantum computation. So combining the evidence from numerics and also from experiments, we come to a very central theoretical question that really motivated the recent work that I've done. And this is, how do we theoretically describe the competition between superconductivity and fractional Chern insulators? And in this talk, we will focus on tuning the periodic potential at fixed filling. Of course, there's also a very interesting story about how you get superconductivity from doping the fractional Chern insulator, but I won't touch on that for the most of today's talk. So to make the question more constrained and more concrete, we can ask, if we specialize to just a single FCI, let's say the nu equals 2/3 FCI in the previous examples that we discussed, what kinds of superconductors can we reach through a continuous transition? Okay, we can never be sure that this transition is truly continuous, but at least at some mean field level, can we find such a continuous transition? And the second question is, what observables can we distinguish between different types of FCI-SC transitions? And our answer is the following. So instead of using the usual abelian gauge theory description of fractional quantum Hall states, we will actually see that it's useful to think about a more complicated U2 gauge theory description of James states. So I emphasize that U2 is a non-abelian gauge group, but just because it's non-abelian gauge group doesn't mean that the topological order that it describes is non-abelian. So in fact, the James state is abelian, so we need to use a more complicated non-abelian gauge theory description. So using this description, we can recover actually 5 different paths from the single James state at nu equals 2/3 to various kinds of different superconductors. Some of them are charged 2e, some of them are charged 4e. So landscape is sort of unwieldy. So today I want to just focus on two examples that are maybe simplest to understand. And I'll comment on the other examples towards the end if people are interested. Yeah, so you see here actually in this square box, there are not two examples, but three examples. But we will actually focus on the two examples towards the very left, because the third example is the conventional one that has already been discussed in the previous literature. Okay, any questions before we move on? If not, okay, here's the roadmap for the rest of the talk. I'll first give you what I call the standard parton construction of the Jane state, which is basically, you should think about it as a lattice version of the composite fermion construction in fractional quantum Hall physics. And I'll tell you how you can get a transition from the Jane state to a superconductor already within the standard parton description. But I'll show you that this doesn't agree with the numerical observation that I showed you in the beginning. So that forces us to consider something more complicated. So this is the U2 construction that I will explain. And using the U2 construction, I'll discuss basically two transitions, one to a 2e topological superconductor and one to a 4e superconductor. If time permits, I'll also discuss the topological order of the 4e superconductor, but if not, that's fine too. I think the message is already contained in the first three parts. Okay, standard parton. Brief review of what Jane state at 2/3 actually is. So we know that at filling 2/3 in the Landau level, the fractional Hall conductance is going to be sigma xy equals 2/3 times this e squared over 2 pi h bar, which I'll set to 1 for the rest of this talk. And the anyon content of the theory is very simple. You have the vacuum, which I call 1, and you have a 2/3, which is the charged 2/3 anyon that's sourced by the 2 pi flux of the external electromagnetic gauge field. And then I have a 4/3, which is just the square of a 2/3. So this sector just by itself is a bosonic topological order. And it has the interesting property that the generating anyon, a 2/3, as well as a 4/3, actually have the same statistical angle. So it's the theta equals 2 pi over 3. In other words, there's an anyon permutation symmetry between these two anyons if we neglect the symmetry enrichment by the U1 global symmetry. And on top of this bosonic topological order, you also have this product with 1c, where c is the physical electron. So taken together, this defines the full content of quasi-particles in this fractional quantum Hall state. I should comment that this is, of course, equivalent to thinking about the particle Hall conjugate of the Laughlin state at nu equals 1/3. And this will be important for some of our discussions. So what's the standard construction for this Jane FCI that will give us a gauge theory description of the topological order? So the construction is you take the electron operator on the lattice, and for every lattice point, I rewrite it redundantly as C equals F1, F2, F3. So of course, this redundancy means that there's gauge transformations of the F variables that will leave the decomposition invariant. Specifically, you can observe that if I rotate F by an arbitrary SU3 matrix, right, the C will be left unchanged. So in the usual fractional quantum Hall physics, we will choose a mean field ansatz for these the states that the F particles form, which breaks the SU3 gauge redundancy down to a diagonal U1 times U1 gauge redundancy. So the meaning of this is that the diagonal U1, it rotates F1 by some phase, and it rotates F2 by a different phase. That's the two U1s. And F3 is now forced to rotate by the sum of the phases of F1 and F2. Of course, there's also a minus sign. So to capture this gauge theory, I'll have to introduce two dynamical U1 gauge fields, which I call A1 and A2. And of course, because they act on F1 and F2, I'll couple F1 to A1, and I'll couple F2 to A2. And F3 will couple to minus A1 minus A2, so that the product does not carry any gauge charge. Now, I have to choose a symmetry enrichment of this theory because there's also an external electromagnetic gauge field, capital A, which encodes the global U1 symmetry. So it actually doesn't matter how you assign it. So here I'll just assign it to F3 for simplicity. So what's the ansatz that we need to get the Jane FCI state? We know that at nu equals 2/3, the system sees a total magnetic field, which I'm labeling as capital B. Now, the ansatz that Jane chose is to choose the magnetic field of A1 and A2, which I call B1 and B2, to each be 2B over 3. Okay. So then that forces the magnetic field seen by F3 to be B3 equal to minus B over 3. So if you just work out the algebra and, because the electrons are at lattice filling 2/3, you see that F1 and F2 partons are now at filling 1 relative to these emergent magnetic fields B1, B2. And F3 is at filling minus 2. Okay. So a very natural mean field state you can consider is you put F1, F2 into integer quantum Hall states with Hall conductance equal to 1. And F3 will go into an integer Hall state with Hall conductance minus 2. So because the integer quantum Hall states of F1, F2, F3 are all gapped, you can integrate out these gapped degrees of freedom and generate an effective field theory that's written only in terms of the emergent gauge fields. So after some algebra, you can convince yourself that this simplifies to just the usual description of the Jane state as 1 over 4 pi ADA. So this is you think about this as a totally filled Landau level. And then there's the level 3 Chern-Simons term, which encodes the particle Hall conjugate of the Laughlin state. So you can check, for example, that the Hall conductance of the state described by this Lagrangian is precisely 2/3, and the topological order will follow from the level 3 Chern-Simons term for this U1 gauge field alpha.
A question?
Yes.
Can you remind us of the charges of F1, F2, and F3?
Charges under the physical gauge field or the internal gauge field?
Like the emergent gauge field, like are they just like integer?
That's here. That's in this equation. So F1 carries charge 1 under A1, F2 carries charge 1 under A2, and F3, yeah, it's just written as in this equation.
Okay.
Yeah. So you should check that, for example, F1 times F2 times F3 should not carry charge under any of the internal gauge field, but it carries charge 1 under the external gauge field, which makes sense because that's the electron.
Yeah. And wait, but if you write it this way, it seems like F3 carries into the charge of the external gauge field.
F3 carry. Yes, that's correct. Yes.
Okay.
Yeah, you can assign it anywhere. So this would have been fine if I put this capital A in F1 or F2. It doesn't actually change the results.
Yeah, it's good. Okay.
Okay, yeah, thanks.
You just basically integrate out F1, F2, right, in your final. Oh, I
Yeah.
guess all fermions are integrated out, I see.
Yes, all of them are integrated out because they're all forming these gap states. Yeah.
Okay.
Okay, very good.
Oh, and what is alpha?
Yes?
What is alpha?
Oh, alpha is just you do some algebra and you can rewrite everything in terms of a single gauge field, not two.
So alpha is a linear combination of the gauge field?
It's actually not a linear combination. You have to introduce some auxiliary gauge field to do this. But yeah, I didn't show the algebra, unfortunately. But yeah, we can talk about it offline if you want.
Okay.
Yeah, it's not too complicated, but it's also not a direct linear combination.
Okay.
Yeah. Okay. So now let's ask, if I have this construction of the Jane state, how do I get out of it, right? And there's a very fun game that you can play if you're too bored, and this is called the parton band inversion. So you imagine early on, I told you that each of the F particles are forming an integer quantum Hall state. In other words, it's fully filling some Chern bands with some fixed Chern number. Now, what if I go through some kind of band inversion transition for some of the partons? Okay, so you can do this, for example, if I fix F1 and F2 and I change the Chern number of F3, right? Initially, it was -2. Now, if I go to -1, it turns out I get an integer quantum Hall state. Go to 0, I get a neutral state with some residual topological order. And if it goes to 1, I get a Laughlin state. And it goes to -1, I get a trivial insulator. So there are sort of all sorts of possibilities that you can imagine obtaining by just modifying the Chern numbers of various partons. But is there any constraint, right? We can ask, are all of these transitions really possible? And the answer is, of course, no, Okay, and that's because the system that we have actually has lattice translation symmetry. Okay, so that's what we assume. The magnetic field is such that there is exactly one flux quantum per unit cell, so there's exact lattice translation symmetry on the original lattice. And this can be easily seen within the parton description because, like we said earlier, each of the parton actually doesn't see the full magnetic field B that was externally imposed. Instead, it sees a fractional magnetic field, which is 2B over 3. So what is the meaning of seeing a magnetic field of 2B over 3? That means that if you look at the translation, the action of translation symmetry on these partons, they will no longer commute with each other. Right? This is the standard Hofstadter problem. And specifically, when you see a fractional flux with a denominator, which is 3, then the unit cell of each of the parton needs to triple, which means the Brillouin zone, the momentum space in which the parton dispersion is defined, needs to be 1/3 the size of the electron Brillouin zone. And within each of the reduced Brillouin zone, there actually, this projective action of lattice translation will enforce a threefold degeneracy in this parton dispersion. What does this mean? This means that if you want to make the parton go through a band inversion transition, then this band inversion transition must have energy gap closing at 3 points in your momentum space instead of just a single point. In other words, the Chern number, jump, across this parton band inversion transition must be an integer multiple of 3. So this dispersion is not just, something I pulled out of a hat. People have actually done numerics to look at the dispersion of anyons in fractional Chern insulator in some recent works from both Harvard and Princeton. And indeed, this is the kind of thing they see. It's that the anion dispersion has a very interesting degeneracy that you might not have expected from the microscopic band dispersion. So given this lesson, then already many of these transitions can be crossed out, right? For example, the transition directly from C3 equal to -2 to -1 is not possible because the jump is 1, not 3. So if you then look at it, okay, the options become very limited. One option is you take C3 from -2 to 1, and this actually takes you from the Jane state to the Laughlin state. So the Hall conductance goes from 2/3 to 1/3. And this transition actually directly describes quantum electrodynamics in 2+1 dimensions. And this was pointed out in some earlier work from 2018. Another interesting example that has also been considered in some work from last year is if I fix C3, so I don't change C3, but I change C1 from 1 to -2. And now the state you get is actually a superconductor. And again, the transition is described by some quantum electrodynamics theory, but now also with some residual Chern-Simons term for the electrodynamic gauge field. So what is the theory, right, for the superconductor with this assignment of Chern numbers? If I, again, because each of the parton is forming a gap state, I can integrate them out. And you see that the topological quantum field theory will reduce to something very simple. You again have a single U1 gauge field alpha, and it couples to the external gauge field through this mutual Chern-Simons term with coefficient 2. But there's nothing else, right? There's no other Chern-Simons term for the dynamical gauge field alpha. So what this really is a particle vortex dual description of the charge 2 superconductor that we're familiar with. And this is very easy to see from the mutual Chern-Simons term because when you integrate out alpha, it essentially gives a Meissner effect for this external A gauge field. And the coefficient 2 tells you that the condensing object carries charge 2, not charge 1. So this is the first example of a description directly have a transition from the Jane 2/3 state to a superconductor. But unfortunately, as you can see, this is a very simple state. It's an abelian state, and it has a chiral central charge, which is -2 encoded in this second term, which only depends on the background gauge field. So this chiral central charge obviously does not match with the numerics that we have seen earlier, which sees the odd winding of the order parameter around the Fermi surface. So to fix this, I hope the whole point of going through this wrong answer is to convince you that the standard parton constructor is insufficient. Okay, we have to go beyond it. We didn't introduce U2 because we wanted to have fun, right? We introduced U2 because there's no other way out. So now let's come to that.
Hi, Darius.
Construction. Yes.
Yeah, a small question. When you say there's a C minus equals to -2, do you assume there's a gravitational Chern-Simons term that's matched by Wiedemann-Franz law?
Yes, so there is a gravitational Chern-Simons term, which I just didn't write here because I didn't want to talk about the metrics, etc. Yeah. So you should think, yeah. In fact, this A, if you wish, this A is a spin C connection. It's not a U1 gauge field. So it has to be accompanied by the gravitational Chern-Simons term.
Okay, got it. Thanks.
Yeah. Thanks. Okay, so let's do the U2 theory. So it turns out there's actually two different U2 descriptions, and they're related to each other by a particle-Hall conjugation. So the first U2 description is I do the same parton as I did before, but I just relabel F3 as psi to emphasize the gauge structure. So instead of choosing a mean field that only preserves the U1 times U1 gauge invariance, you see I can choose a mean field such that the F sigma sector, so the F1, F2 sector, is actually U2 symmetric. This is consistent because if I want both F1 and F2 to form an integer quantum Hall state with Hall conductance 1, it's possible to construct a singlet state with this Hall conductance. So if I choose the mean field to be U2 symmetric, then the gauge group is enlarged, right? Because in the F sector, I can now do a U2 rotation, which is compensated in the psi sector by a determinant of the U2 matrix. So given this U2 description, I can now write down a U2 gauge theory in which F couples to alpha in the fundamental representation, and psi couples to minus trace alpha. So this trace alpha is basically the logarithm of this determinant. And moreover, I'll do my charge assignment so that I put positive A charge on F1 and F2 and a negative A charge on psi, such that the product of F1, F2 psi still carries charge 1. So actually, how you do this charge assignment precisely doesn't really matter. This just makes it easier for me to write down the later manipulations with the field theory. So let's see how this works out. So if I put F1 and F2 in this integer quantum Hall state, what I will generate now is a non-abelian Chern-Simons term for this U2 gauge field alpha plus A. And it has the form as written here. And the level 1 tells you that the Hall conductance of each species is actually 1. For the psi sector, on the other hand, we know that we need to put it into a Chern insulator with Chern number -2. So then this comes with a Chern-Simons term, which has a -2 prefactor. Now, putting these two terms together, I get the final Lagrangian, which is what I would refer to as the L1, the first U2 description of the JNFCI. So the second description, we have to use the fundamental identity, which is 2/3 is equal to 1 plus minus 1/3. Okay, the meaning of this is that I would regard the JNFCI as, again, a filled Landau level plus some lattice electrons at filling -1/3. And for lattice electron at filling -1/3, I do this parton decomposition. But now it's actually simpler because that's just the Laughlin state, right? So for the Laughlin state, I want all three partons to see the same magnetic field. So all three of them sees magnetic field that's B/3. And so each of the partons will actually be in this integer quantum Hall state with Hall conductance -1. So we do the same manipulation, right? Now the only difference is that I have to first add in the filled Landau level. So there's an extra 1/4 pi AdA term. But then the rest of it is exactly the same as on the previous slide. I just choose the Hall conductance to be -1 for all three partons. And now I get this second description of the JNFCI, and U equals 2/3. So at this stage, I think it's very natural to ask, how do we know this describes the JNFCI, right? One way to do it is, of course, you can just construct a wave function, but on the lattice, that's a bit difficult. So to see that it really describes the JNFCI, I want to invoke a very interesting recent argument, which involves it's an idea of doing bootstrap for topological order. So you impose some constraints on a given topological order and ask whether, you impose certain constraints and you ask what's the minimal topological order that's consistent with these constraints. So actually the JNFCI is one of these minimal topological orders. So if we demand that the system is at lattice filling 2/3 and has Hall conductance 2/3 and chiral central charge 0, the Jane state is actually the unique minimal topological order. So this was shown in this recent paper from Meng Chen and collaborators. So all we need to do is we take these two Lagrangian and we check their Hall conductance, we check their chiral central charge, and we check their torus degeneracy and make sure that it's minimal, meaning that the degeneracy is 3, and then we'll be done, okay? So what I can promise you is that both of these things, you can easily check that all 3 of these properties hold, and indeed they describe the same Jane 2/3 state as the abelian gauge theory description. So we should give some name. Yes.
The L2, like the second Lagrangian that you write down, I mean, it has a self like Chern-Simons term for capital A, right? So
Yes.
Does this still have like vanishing chirocentric charge?
Yes, it does. Yeah. So actually the non-abelian part in the second term contributes chirocentric charge 2, and that's subtracted off by the background.
I see.
Yeah. So both of these you can check that it works out.
Oh, and the first one, the non-abelian part has 0 chirocentric charge?
That's right.
Okay. I see.
Yes. Yeah, so just to set the notation straight, so I'm using this Seiberg-Witten notation in which for U2 gauge theory, you have 2 levels. And the first level corresponds to the level for the SU2 part, and the second level corresponds to the U1 part. And this makes sense because the Lie algebra of U2 decomposes into the SU2 and U1 part. But of course, as a global group, there's an additional Z2 quotient, which is important for getting the correct topological order. And the level labeling is such that, these SU2 sector can have plus minus 1, depending on whether the non-abelian Chern-Simons term has level plus minus 1. Okay, so from this description, we can already see how to get a superconductor, okay, without going through any of the further field theory manipulations. So if we work with the first Lagrangian, right, if the first Lagrangian, we know that the partons, the F partons, both form C equals 1 Chern insulators, and the psi parton is in C equals -2. So now if I remember the old rule that across a band inversion transition, the parton Chern number has to jump by plus minus 3, then I can make the F Chern number jump from 1 to 4. Okay? And if you do that, you will actually find that the resulting state is a charge 4e superconductor. And the charge 4e superconductor has some interesting topological properties. In particular, its vortices will trap parafermion zero modes. And on the other hand, if you work with the second Lagrangian, where all the partons are forming C equals -1 Chern insulators, now if I make F jump from -1 to 2, I'll get a charge 2e superconductor. And this charge 2e superconductor will actually have an odd angular momentum, so it has a half-integer chiral central charge. And so far, I haven't explained to you why these corresponds to 2e and 4e, but hopefully, maybe it's a little bit convincing that all the Chern numbers are doubled when you go from 2e to 4e. So it's not crazy to imagine that the charge condensates are also different. So with this preview in mind, let's briefly go through the construction of the field theory for the 2e and the 4e case. In the 2e case, just as a brief review, we want the parton F1, F2 to each go through a Chern number jump transition by plus minus 3. And this is because we want to preserve the U2 gauge invariance that rotates the partons F1, F2 into each other. And if you just write down this field theory, right, I erase the -1 used in the previous construction for the Jane state, and I replace it with a 2. So if you do that and you add these two terms together, you get this Lagrangian that I've written down in the bottom line. So what is this Lagrangian? Let's analyze it a little bit. So this Lagrangian in the Chern-Simons notation is actually U2 level -20 times some additional U1 sector that's basically the background Chern-Simons term, 4 over 4 pi ADA. So let's just focus on the U2 part, okay? The background part just shifts the chiral central charge. It doesn't, by an integer amount, it doesn't affect the half integer part. So how do I extract the Chern-Simons level? Well, I could decompose this alpha gauge field into a abelian part and a non-abelian part. The non-abelian part only appears in the first term, and that has a Chern-Simons level -2. Notice that my convention is sort of inverted. But for the abelian part, both the first term and the second term will contribute, right? But in the first term, it's a diagonal matrix, alpha 0, d alpha 0, right? Where alpha 0 is the diagonal component of alpha. And the first term actually has a coefficient 4 over 4 pi alpha 0, d alpha 0. Whereas the second term has a coefficient of minus 4 over 4 pi, because each trace gives you a factor of 2. So overall, the abelian part has a Chern-Simons level of 0, whereas the non-abelian part has a Chern-Simons level minus 2. So that explains the notation here. Moreover, there's a coupling of the abelian part, like trace alpha, which is 2 times alpha 0, to the external gauge field A. So this term tells you that the abelian part describes a charge 2 condensate. But then you might think that the non-abelian part contains some non-abelian topological order, which is SU2 level 2. So now the key point is that U2 is not SU2 level 2 times U1, right? So U2 involves this discrete quotient. So the real topological order we have is SU2 level minus 2 mod Z2. And what is that topological order? So this topological order, if we start with SU2 level minus 2, it has 3 anyons, and the Z2 quotient corresponds to condensing the J equals 1 anyon. Okay, this is the language of condensation can sometimes be confusing, but in this context, it's quite simple. When you condense this anyon, it confines the only other non-trivial anyon that braids with it, which is the J equals 1/2 anyon. So then there's nothing left. Okay, so at very least, we should expect that this topological order is trivial. So it can at most be an invertible phase of matter. And indeed, it is an invertible phase of matter, and its chiral central charge is actually just given by the chiral central charge of SU2 level minus 2, which is minus 3/2, okay? Because this procedure of anyon condensation does not modify the chiral central charge of the uncondensed phase. So you may ask, okay, how do we make the SU2 level minus 2 come back? And it does come back, and the way it comes back is that if you insert H over 2e vortex, a superconducting vortex, into the system, that is a confined excitation of the system, so it's not a real quasi-particle, so it doesn't contribute to the topological order. But if you force this H over 2e vortex into the system, it actually traps the J equals 1/2 quasi-particle, which is a non-abelian anyon. So this is precisely what you should expect for a strong charge 2e topological superconductor, is that at each vortex core, you're trapping a Majorana zero mode, whose braiding with each other has some modified version of the Ising braiding statistics. So that's the 2e superconductor, and I hope I've convinced you that this is indeed what happens through this one pathway for the first U2 construction. Now, how about the second one? In the second one, again, we go through the same procedure and we just replace 1 with 4. Okay, so if you replace 1 with 4, you see that you basically, for the U2 part, you just get exactly what we had on the previous slide, but with all the Chern-Simons levels doubled. So with the Chern-Simons level doubled, then with the Chern-Simons level doubled, you clearly see that now the charge condensate is going to be 4e instead of 2e, because the mutual Chern-Simons term level is now 4. And now you can also check that the topological order of this theory is U2 level minus 4, 0, instead of U2 level minus 2, 0. So it still describes a superconductor, but it has a richer topological order. So this gives us two construction of Jane-SC transitions, but what I haven't told you is, is there a simple physical observable that distinguishes these two transitions? And indeed there is, right? If we look back at what's really going on at the transition, right? Some partons are undergoing this parton band inversion transition, which is this F sigma parton. And in these two different descriptions, it turns out that before you hit the transition point, the anyon that's sourced by the F sigma parton are actually different. So in case 1, where we get the charge 4e superconductor, right? The anyon that's sourced by F sigma is the charge 2/3 anyon. It's not the charge 1/3 anyon. So if that's the case, then when F sigma goes through a band inversion transition, the charge 2/3 anyon gap is closing, but the charge 1/3 anyon gap remains open. So if I only have charge 2/3 anyon gap closing, that means the electron gap stays open because you cannot construct an electron out of just collections of charge 2/3 anyons. So that's the scenario we have in the Jane 4e transition, is that the electron gap stays open and the Cooper-Parrott gap closes, as in the diagram on the right. But the situation is very different, right? If you go to the diagram on the left, for the Jane 2e transition, the F sigma particle actually sources the charge 1/3 anyon. So then both the electron gap and the Cooper pair gap would have to close. So that's the diagram shown on the left. So this produces a very simple diagnostic that we can look for in numerics, and also, experiment is a bit of a fantasy, but at least within numerics, you should see that across one of these transitions, the electron spectral function or the electron correlator is going to have a larger and larger correlation length as you approach the critical point, whereas in the other case, the electron just stays gapped. Okay, so having explained these transitions, we can come back to numerics and see what we have been able to achieve. So what we have done is constructed, at least in the 2E scenario, we have a topological superconductor which indeed has half-integer chiral central charge instead of integer chiral central charge. So this is one of the puzzles that can be resolved by our theory. And moreover, across this transition, the electron gap does close across the JNSC phase transition. So there's some preliminary evidence from the DMRG numerics that the correlation length in the electron sector is appearing to diverge as they approach the critical point. But of course, it's very hard to make that statement precise given the finite size of the system under study. So it will be very interesting to explore this kind of transition using more high-powered, large-scale numerics, perhaps with some assisted by neural quantum states. But there is some lingering puzzle, and I have to address this, which is that the superconductor seen numerics, if you just apply the standard BDG Chern number counting, it appears to have a chiral central charge that's -1/2 instead of 5/2. So it differs by an integer, which is slightly better than differ by a half integer. But still, I think it's important to really settle the question of what is the chiral central charge seen numerics in a way that's independent of just directly extrapolating from the weak coupling BDG intuition. Okay, they don't have this independent way to measure the chiral central charge yet, but hopefully this will be possible in the future. Okay, how am I doing on time?
You still have 8 minutes.
8 minutes. Okay, so 8 minutes, I think I want to briefly discuss the topological order of the 4E superconductor. So let's come back to this 4E superconductor Lagrangian that I wrote down. And as I said before, the topological order, you can think about it as U2 level 4, comma 0. Okay, and this is SU2 level 4 times U1 level 0 mod Z2, where the U1 level 0 just described the superconducting condensates, the gapless Maxwell theory for the abelian part of this U2 gauge field. So what we should really focus on is the topological order SU2 level 4 mod Z2. So SU2 level 4 as an NEL theory has 5 quasi-particles. It has the vacuum, which is 0, and it has all the spins, SU2 spins up to j equals 2. So 1/2, 1, 3/2, and 2, where 2 is an abelian anion, which squares to the vacuum. So the Z2 quotient, what it does is that it condenses the j equals 2 quasi-particle. And this was discussed at length in the pioneering paper by Bayes Slingerland about anion condensation. And what does this condensation do? So intuitively, if you condense j equals 2, then it first identifies j equals 2 with the vacuum. Okay, j equals 2 itself is no longer a non-trivial anion quasi-particle. Moreover, because j equals 2 braids non-trivially with 1/2 and 3/2, the condensation of j equals 2 will confine these half-integer quasi-particles. So the only thing that's left is the j equals 1 quasi-particle. And here something really interesting happens, because the fusion rule in SU2 level 2 is such that when you take 1 and multiply by 2, you get back 1. Okay, so whenever this property holds and you condense 2, you have to split 1 into 2 separate abelian quasi-particles. So it turns out you can work out the splitting precisely, and the remaining theory with just vacuum 1 plus and 1 minus, these 3 anions, is actually identical to the Jane topological order. It's the bosonic sector of the Jane topological order, meaning that if you don't include electrons, then the Jane topological order is exactly equivalent to this topological order realized by the superconductor. So now we can ask, okay, what is the defect structure or what is the vortex structure in this theory? Just like we asked for the charge 2e superconductor, there we found that if you insert an h over 2e vortex, you actually trapped a Majorana zero mode. So now what we find in this case is that the elementary vortex, which is now an h over 4e vortex because you have a charge 4e superconductor, it doesn't trap a Majorana zero mode. Instead, it traps a Z3 parafermion zero mode, such that when you fuse two of these h over 4e vortices together, you have three possible fusion channels corresponding precisely to the three possible abelian anyons that I presented on the previous slide. So I think this is very exciting to me because previously people have proposed parafermion zero modes in many different contexts, but they're mostly confined to the edges or some kind of discrete symmetry defects. And there are some concrete proposals, both for fractional quantum Hall with superconductor proximity effect, and also for various kinds of discrete symmetry defects like layer exchange defects in the ZN-torque code. But here we have I think, even simpler example, right? We really just have a superconductor with a U1 symmetry, but the role of the discrete symmetry defect is played by a spontaneously broken continuous symmetry. So you don't start with a system with a discrete symmetry. You start with a system with a U1 global symmetry. And only when the U1 is spontaneously broken do you get this discrete symmetry defect structure. And in that case, the discrete symmetry defect precisely corresponds to the vortex of the U1 global symmetry. So this, because it's a U1, the vortex energy cost is logarithmic, not linear in size. And also it can be more freely moved around than these discrete symmetry defects. So I think there are many questions that we can explore along these lines, and I don't have time to discuss all of them. We also haven't thought through all of them. It's exciting things to think about in the future. I just wanted to point out that it's amazing to me that you get a transition from a Jane to 4e superconductor, and the superconductor has very unusual properties that allow it to do quantum computation. Okay. So before we depart, I just wanted to come back to this phase diagram and briefly comment on two things, right? One thing is, so far we've only covered the left half, right? There's these two possible paths, either to a 2e superconductor with C minus equal to 5/2, or this 4e superconductor with C minus equal to 4. There's a mirror of these two transitions, okay? Also to, another 2e superconductor and another 4e superconductor. And these mirror transitions are slightly harder to describe, but they are described in the paper. So especially the first paper with Sento that you can check out. And there, the transition theory is more complicated, right? In the previous example we talked about, basically, it's a band inversion transition for F sigma, which when you add the gauge field, is sometimes called a quantum chromodynamic CS Chern-Simons transition, so QCD Chern-Simons theory. But in the mirror plane, you'll actually have more complicated transition involving both abelian and non-abelian gauge fields. So I think it would be fantastic if some work can be done in the future to see whether any of these transitions are really continuous, or are we just misled by the intuition from mean fields. And finally, I want to say that, parton band inversion can seem like an endless game that you can play. Right? Where's the physics, right? You can have infinitely many different parton constructions. In principle, they could lead to infinite different field theory descriptions of the same topological order, and also infinitely many transitions out of them. So how do we know that if any of this is physical? I don't have a complete answer to that, but all I can say is that I have tried personally order 10 different constructions, and they all led to the same set of transitions. And also, if you just look at each of the Chern-Simons description we have, independent of which parton it comes from, then you can exhaust all possible Higgs transition, Dirac critical points, blah, 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 and they will all reduce to the examples that we've considered here. So in some sense, within the landscape of theories for which we know how to construct topological quantum phase transitions, I think this is a pretty exhaustive list. But in some sense, this is a win-win, because if there are more examples that go beyond this, then I think they will likely lead to new kinds of topological phase transitions that's beyond the framework of either Higgs or Dirac criticality. So if such a thing is discovered, we're wrong, but that's okay, because everybody will learn something from it. Okay, so I'll just leave with this slide, which is some future directions, and I think we're about, yeah, it's about time to start taking more questions. Thank you very much.
So if there's any further question from the online audience?
Maybe just a more physical question. So you motivated all of your study from experiment that basically tunes the interaction strength, right? Is it
Which experiment? Are you referring to the rhombohedrographene or the twisted
yeah,
MIT?
like when you have more potential and you don't have more potential, like
Yes, yes. So that's tuning the strength of Moray potential.
yeah, more potential. So is there a direct kind of manifestation of that in field theory?
Yeah, I
Because I mean,
don't.
it's just basically the potential that tunes like the banding version, right? Like, is there?
Yes. So you're right that from the perspective of the partons, indeed, this transition is driven by some tuning of the parton band structure. And what's not clear is whether that's related to tuning the microscopic band structure, which is determined by both the quantum geometry and the strength of the periodic potential. So from the field theory, there's no direct way to see that, right? The field theory is just constructing possible transitions out of this state, but I don't know which microscopic tuning will lead to this transition. The only thing I can say is that in numerics, there is one particular tuning, right, in both Taiga and Mike Zolotel's numerics and numerics from Liang Fu's group at MIT. They see that with certain microscopic parameters, you can tune between the fractional Chern insulator and the chiral superconductor. But I don't know.
So you have
Presumably, there are
faith
other
that
tuning
that's,
parameters too.
yeah. So you have faith that maybe it's a small leap of faith that this tuning up that you're using like numerical study is the same one that's going to drive like banding version transition in like your partons.
Yeah, I think it's I think it's not even a small leap; it's a big leap.
Yeah.
It's not we're not saying that if you suppose you give me specific microscopic model with specific tuning parameter, I cannot predict using field theory which transition you're going to go through.
Yeah, but
Right.
you can certainly analyze, for example, which term will become what term, like from lattice model to field theory. Maybe it's not a direct kind of identification, but there are arguments you
Yeah.
can make, like from symmetries or
Uh-huh. Uh-huh. Yeah, I think right. So that can be attempted if you can start with the construction of the Jane state that gets good energetics by, suppose you directly take the microscopic model of um, say electrons in directly do the parton decomposition and do a mean field. And if that matches the experiments well already for the Jane state, then you can hope that when you tune the microscopic potential, you can get a good sense of how the parton band structure is evolving. But we didn't start there. So I think there's potential to do that, but that requires more work than what we have done so far.
Okay, thank you.
Yeah.
Okay, so we don't have any further question. Let's start the speaker again. Okay, forget about the next one. And hope to see you on the corner if you come back to it.
Okay, should I stop share, I guess?
Yeah.
Okay.
Thank you.
Let's cannot.
Yeah, thanks.
Thank you.
Yeah.